All right, so I think I'm going to move on to our next topic. And our next topic is extremely important in quantum mechanics, and it's called angular momentum. Okay. Our next topic is angular momentum and its representations in quantum mechanics. So this is a topic that is not just important for physics, but also for mathematics. The technique that I will go over today about deriving the representation of angular momentum in quantum mechanics play an important role in group theory. It's one of the most central things in the theory of representations of Lie algebra. Okay, so what is angular momentum? Classically, you know this. Classically, angular momentum is given by r cross p, right? Where r is the position vector. Okay, so question number one, is angular momentum a vector or is it a pseudo vector?
It's a pseudo vector as far as I know.
Okay, what is a pseudo vector?
The cross product, if we change it like momentum times momentum x r would give me minus the results, I think. I'm not exactly sure, to be honest.
Okay, so there is a transformation called parity, okay?
Okay.
And what parity does is that it takes all the spatial position of a particle to its negative, okay? It's a mathematical transformation. If a vector, say three-dimensional vector v, flips like x, then it's called a vector. But if a vector, say A, under parity does not change sign, then that's called a pseudo vector, okay? So what is momentum? Momentum is the time derivative of a particle times its mass. So under parity, t does not change, m does not change, but p goes to minus p. So angular momentum is r cross p, then under parity, it goes to itself because there are two minus signs, right? So angular momentum is invariant under parity, and therefore it's a pseudo vector. It's a pseudo vector. It's
so the
also
invariance under the
parity.
invariance under parity is the reason why it's a pseudo vector.
Yeah, exactly. And it's also called an axial vector. Okay. So, okay, so now we know that in quantum mechanics, the position operator in the position representation is given just by the numbers, right? The coordinates of the particle. But the momentum operator in the coordinate basis is given by minus I h bar, the gradient operator. So in quantum mechanics, the L operator is going to be given by the way L, it will be replaced by an operator which will be given by R cross P. So now if I look at the components of this, because this is now a vector operator or an axial vector operator. By vector here, I mean it has 3 components. Right? So under rotation, an axial vector acts like a vector. Right? Because under rotation, if I do a rotation, then the components of L will change by, say, L, some rotation vector acting on L. But it's under parity that it behaves in a different way from a vector. Okay, coming back to our axial vector operator, which is angular momentum, we can look at its 3 components, and its 3 components are Lx hat is y hat p hat z minus z hat p hat y. Now, I could have written this as p z hat y hat, and the second term, I could have written it as p y z hat. Can someone tell me why?
They're not commutative?
No, they do commute.
Oh, okay.
Because the thing is that if I look at the position operator, say x, and it's
right.
a vector operator, so I take the ith component of it, and I take the momentum operator, say take the jth component of it, and compute the commutator of this. It's I h bar delta ij. That means that it's only the x component. I should say x here. X and px will not commute, but x and py will commute. Okay. So I could have written this. So because this is y and z, pz, they will commute. So I could have written it, but conventionally I'm writing it like that. Okay. So let's carry on with the other. So let me just write down all the components. Lx is going to be y pz minus z py. It's easier for me to write it in a particular order. So it's z px. So these are all operators. Pretty soon I'm going to drop the carets and the hats because it just gets very boring after a while. And you should be able to say which is operator, which is not from the context. Okay. So these 3 equations, of course, I can write them like this, but I can also write them using the Levi-Civita symbol. So I can say L, ith component of L, is given by epsilon ijk, the Levi-Civita symbol, and then say, let's call it, say, R, the jth component of R times P, the kth component of P. So you guys should be able to show that, and because there's a repeated index j and k, there has to be a sum implied, okay? Sum implied over repeated indices. Okay, so if you have never done this sort of before, it's good to do it once at least. So let's take I to be x, okay? Then I have Lx here. Then epsilon has x here. Then j can be y. If j is y, k has to be what? Z, right? There's no other choice. So here R will have ry, and then P will have pz. But this is just one option. There's a sum over all possible values of j and k. So I have to add to it epsilon x. Of course, the first index is is fixed, but the second index y can be z. If y is z, then the third guy has to be y, because for the Levi-Civita symbol, all the indices have to take different values. Then r here is going to be z, have the index z, and p is going to have the index y. Now, conventionally, epsilon x, y, and z is +1, and this guy just comes from this by one permutation. So epsilon x, z, y is going to be -1. So we can see that L of x is going to be ry, which we can just write it as y, pz, minus rz, we can just write it as z, py, right? Which is exactly what we have here. Okay, so you should be convinced that, you can do two more. You can be convinced that this is a shorthand for these three equations. Okay, any questions?
No,
Sir, why are we assuming J not to be equal to K? Or
Well, because then it's 0. Epsilon is 0.
oh, right.
The epsilon tensor has the property that whenever you have x, say y, this is 0. In epsilon ijk is 0 if, say, j is equals to k. Okay, that is a property of the Levi-Civita symbol. Okay, the Levi-Civita symbol is what you use when you're taking cross products. You know that, right?
Yes, sir.
Okay, look into that, think about it, do some examples, try it, and then if you have questions, please let me know, okay? Okay, so now what we're going to do is that we are going to use our fundamental commutation relationship, our fundamental commutation relationship. What is our fundamental commutation relationship? It's R, so I'm going to drop the carets, okay? Ri Pj is equal to I H bar delta Ij, okay? And we can now calculate what the commutator of Li and Lj are. And with a little bit of algebra, which I leave for you to do for yourself, i.e. show, this is going to be epsilon ijk lk. Okay, this is a very important relationship. It's called the angular momentum algebra. And it's a Lie algebra, and it's a show. Okay, so you will need a little bit of technical stuff. Let me just give you some hints. One thing you will need, because these are now, these are products of operators, right? So you will need the fact that if you have a product of two operators and you take the commutator with another operator, then you get something like A commutator plus of BC plus commutator of AC times B. Okay, so that you can then use your fundamental commutation relationship to work this out. All right. So this is the famous angular momentum algebra, and we have derived this angular momentum algebra using the position representation, right? Because we took L to be in terms of its definition So it's in the position representation of. So that means that these angular momentum operators act on wave functions, right? So this will act on some wave function. So that means that this is an infinite dimensional representation of the angular momentum operator. Because as we saw, we can think of wave function as an infinite dimensional vector, components of an infinite dimensional vector. By the way, the other thing to observe is that, okay, let me just make some comments formally so it sticks. One comment is that, we derived the angular momentum algebra using the position representation of L. Thus, this is an infinite dimensional rep of the angular momentum algebra, and the operators act on wave functions, or because, yeah. The other comment I want to make is that Lx and Ly do not commute. Lx and Ly, according to the angular momentum algebra, gives me I h bar Lz. So what does it mean for the simultaneous measurement of Lx and Ly? Can we do it with arbitrary precision?
We can't simultaneously measure them.
Right, because we saw that if two operators do not commute, then the generalized Heisenberg uncertainty relationship tell us that we cannot simultaneously measure them with arbitrary accuracy. So in mathematical terms, this also means that we cannot find simultaneous eigenstates for these two operators. So we cannot find an eigenstate, say alpha beta, such that Lx acting on alpha beta gives me alpha of alpha beta, and Ly acting on the same state gives me, say, beta alpha beta. This cannot happen because they don't commute. Lx and Ly don't commute, okay? So these are the two comments I wanted to make.